Hello, hello, hello. Okay, good morning, everyone. We are going to continue with Rafael's talks. He will tell us about cosmic ray propagation today. Rafael, please.
Yeah. So thanks. Good morning, everyone. The topic of today, it's a bit different from the program. In the program, there was a separation between galactic and extragalactic, but considering how things are going, I decided to unify all aspects of propagation. So this might take 2 lectures, and I'm going to talk about both galactic and extragalactic at the same time, of course, making clear the distinctions. Okay, so what we are going to see today, it's pretty much we are going to review a bit of the particle interactions that take place when cosmic rays are propagating in the universe, whether it's in galactic or extragalactic environments. We are going to see, review some of the interactions and discuss them in a lot more detail. I'm going to show you some of the main aspects like mean-free paths related to propagation, which tell you how far the particles, the cosmic rays, can propagate in a given environment. And then I'm going to talk about how cosmic rays travel in magnetic fields, how they propagate in magnetic fields. I actually don't think I'm going to have time for this because, as you noticed, in the other days, I'm not very good with time. But yeah, I do hope to get to this at some point. I'm actually definitely covering this. I just don't know if it's today or tomorrow, especially the more technical details. Okay, the basics of propagation. So, usually what we have is a source somewhere in the universe, whether it's in our galaxy or outside our galaxy, it doesn't matter. This source emits a cosmic ray. This line is curved for obvious reasons because, well, cosmic rays, they are deflected by magnetic fields because they are charged particles, and we know there are magnetic fields all over the universe. And then they travel in the universe, they are deflected by extragalactic magnetic fields, or in the case of our own galaxy, by galactic magnetic fields, and then they reach Earth. Okay, during their propagation, some interactions might take place. These interactions might lead to the disintegration of the primary cosmic ray nucleus in a process, well, a common process, it's like photodisintegration that we are going to see later on today. And these processes, they might also lead to the production of neutrinos and photons. If this happens during the propagation of cosmic rays, in particular, cosmic rays of ultra-high energies, above 10 to the 19 electron volts in this case. If this happens during the propagation of ultra-high energy cosmic rays, we call these particles cosmogenic particles, although I think the name cosmogenic can be used for any energy. But yeah, these are commonly known as cosmogenic neutrinos and cosmogenic photons. Okay, so in general, if we want to model or to understand how particles propagate in the universe, we have to consider a few things. First, we need some astrophysical inputs. This helps us build the model. These inputs, they are things that have to do with the source or with the initial conditions, if you will. So this means that we need to know how the particles are injected, so the injection spectrum, the energy distribution of the particles, when they are emitted by the source. We need to know the composition, so essentially if you're talking about cosmic rays, which kind of cosmic ray nucleus you're talking about, if it's hydrogen, helium, or iron nuclei, or if it's another type of particle. For example, neutrinos, it would be the flavors, and so on. This recipe, it's very general. You can use it for propagating any type of particle in the universe. You also need to know the distribution of sources. So like if you're studying just one source, it would be just one source in this case. If you're studying several sources, it would be the spatial distribution of each of these sources relative to each other. And these might have some time dependence. These might evolve together with the universe, so there is some emissivity evolution, which tells you how in time this emission changes. So once we fix this, and this is very important, this is fixed by the model. These are assumptions that we make in the beginning. Once we make these assumptions, then we perform the propagation part, which is the theme of today. So the propagation part, it takes care of, well, particle interactions that I have already mentioned. So this, for example, if you have a cosmic ray proton traveling in the universe, we know the universe is filled with photons from the CMB, the cosmic microwave background, for example, and they might interact. So this is one of the things that we take into account when doing the modeling. There might be some kind of acceleration, reacceleration in the medium, although some people would say this is not part of the propagation. Well, if it's a particle traveling, it's propagating, and if there is acceleration, I think it falls under this definition. So it also takes into account background photon fields. So, I mean, these are photons that pervade the universe. I just mentioned, for example, the CMB, the cosmic microwave background. There are others that we are going to see, like the EBL, the extragalactic background light. Gamma ray people use this all the time in their studies. Background matter fields, so this could be like gas or dust or things that could prevent the cosmic rays from propagating further, and also at the same time they could act as targets for particle interactions. And of course magnetic fields, because magnetic fields, they not only change the direction, but they also sometimes they make, because they deflect the particles, they make the particles travel longer, therefore increasing the probability of interactions. And finally, we fix the astrophysical inputs, so these are hypotheses that we make. Then we perform the propagation. The propagation, it's the actual technical part, the modeling itself. And then once we have this, we usually try to extract some outputs. So we start at the source, we do the propagation up to Earth or wherever you want to do it, and then we have some outputs. The outputs are the usual observables. I mentioned this yesterday. We talk a lot about the spectrum, so the energy distribution of these particles, the composition, because the composition might change during propagation, the arrival directions, so these are the anisotropies, or the arrival times. For cosmic rays, arrival times, they don't, at least they are not human. They are very, very long. They are thousands, millions of years, sometimes. But of course, if you're doing some studies depending on the time scale of your study and on the specific, since this is very generic, if you're doing like gamma rays or neutrinos, this might be very important. And finally, once you fix your hypothesis and initial conditions, you do the propagation and then you extract your outputs, you have to do something with this. You compare with the observations. So the observations here would involve taking your data, understanding your instrument. In the case of cosmic rays, for example, yesterday morning, we discussed quite a lot the physics of air shower, so we need to take all of that into account to reconstruct the observations, and then we try to match what we see with what we get out of the model. Okay, so this is more or less a general recipe for whatever particle you are trying to propagate. What we usually try to do is to mix all these ingredients here, in particular the propagation ingredients. That's what I'm going to focus today. And we try to fit the observations, this is very important, based on models. Based on models, this means that we are only extracting results that are true. The results that we are extracting are only true if our initial hypothesis, which have to do with the astrophysical inputs that we put here, our initial conditions, our assumptions, we only extract meaningful results if this is true. So whatever result you extract in the end, whatever conclusion you extract, they are contingent upon your hypothesis. And although this is obvious, this might lead to errors because many assumptions, they become so widely used. Nowadays, people keep repeating the same things over and over, and we just assume it's true because everybody's doing it, but it's not necessarily true. And of course, if we're dealing with multiple messengers, for example, I'm talking about cosmic rays here, but we might as well be studying gamma rays or neutrinos because, as we have been seeing, the physics of the cosmic rays is the same physics that generates the neutrinos and often the gamma rays. So these are very similar processes. And of course, if we don't know something here, we fix the hypothesis, but if we don't know something in the propagation part, we just scan everything. We do all the combinations of everything that we don't know here. And this is obviously impossible because there are many things that we don't know. But we try as best as we can. And for that, sometimes we have to use like propagation codes. We have, for example, CRPROPA. which can perform propagation of cosmic rays, gamma rays, neutrinos, and so on. But for cosmic rays only, there are also these other codes that people use. And of course, the choice of code depends on what you're doing. If you want speed, you should go for this one, for example. This is very fast because it's just they just do like matrix multiplications, whereas CR-Propa is full Monte Carlo. But if you want magnetic fields, CR-Propa is the only option among these. Yeah, and I'm going to just spend maybe 1 or 2 slides on that because, well, it's a code that I've been developing for most of my academic career. So, of course, I should highlight it a bit. Yeah, it's a public available Monte Carlo code. You can just download it on GitHub. And it's Monte Carlo. It can perform the propagation of like cosmic rays, gamma rays, neutrinos, electrons, and all the connections. So this is a very nice way to self-consistently model all these types of particles that we have. And it's a modular code. So if something is not implemented, you could just go there and write your own module for that. If you have like for example, you are studying beyond standard model physics, you could just go there, write your own module, and use the rest of the code structure. You just plug these little circles, these little blobs here, and yeah, it's very easy to do. It can run in parallel. Yeah, there are several applications that include like feats of ultra-high energy cosmic ray measurements, transition between galactic and extragalactic cosmic rays, study of the diffusion of galactic cosmic rays, like constraints on intergalactic magnetic fields, for example, propagation of particles in galaxy clusters, cosmogenic particles, and so on. So it's very flexible. Okay. Now, the advertising part is over, so let's move on to the actual physics behind. The first part that I'd like to talk now is about the particle interactions. I've shown you this before. Maybe I can do it a bit faster. Oops. Yeah, I've shown you this before, right? Once again, there are a few aspects here that are important. They are the topics of today's and tomorrow's lectures. The deflections in magnetic fields I'm going to do later. I'm going to start with these interactions, which could generate secondary cosmic rays, or which could generate neutrinos or gamma rays, and so on. Okay, in order to understand it, this is where Astroparticle, this is the particle part of Astroparticle. I know many people here are astrophysicists, and others among you are more particle physicists. And others are have an identity crisis. They don't know how to define themselves. But yeah, this is where we mix things. So the way this is usually done is we consider an interaction between two particles. So we have a particle with energy E1. I'm going to call this the incident particle. This is a high energy particle in general, or at least in some frame. And there is a background particle. And they are interacting through an angle theta. The center of mass energy, actually center of mass energy squared, S, for this type of interaction, it's defined as this, where beta, of course, it has to do with the velocity of these two particles, and m are the corresponding masses of the incident and the background particles, and so on. So this is how we compute the center of mass squared energy. If you ever tried reading or checking out a paper, an LHC paper, they are always like collision of proton-proton at square root of s 10 TeV, for example, something like that. It's exactly the same s. It's a Mandelstam variable. I know many of you know that quite well, but I know there are also astronomers amongst you, so I think it's good to review this aspect. Okay, and once we define what the center of mass energy is, so this is a simple scattering. I'm talking about two particles. This is a very simple thing to do. It's the simplest thing after a decay. And the thing that we are usually interested in, it's the interaction length. The interaction length tells us how far particles can travel. Particles like, let's consider the incident particles. How far these incident particles can travel before they interact with some kind of background particles. And to put this in a more tangible way, you could think of the background particles as photons that pervade the universe, like the CMB, or gas in our galaxy, or something like that. And in order to compute this interaction length for a particle of type 1 interacting with, well, in this case, there is an assumption, an isotropic distribution of these other particles. We can write down this equation. I know it's big. I was going to do that on the board, but I didn't want to waste too much time. But yeah, lambda here, it's a length. So this is actually an inverse length quantity. Here, we have the derivative. So we have the background particles. Okay, let's go one by one. We have the relative velocity between the projectile and the target. This is what beta relative is. We have something here, which is the cross-section. This is the particle physics part, at low level. And then we have this photon density distribution, or whatever thing you have. I wrote photon, but it can be anything. If it's photon, then beta 2 is equals to 1. But yeah, this is the density, the target distribution, I should say. Okay, this has units of 1 over volume over units of momentum. Okay, and this relative velocity is given by this expression where capital P, it's the momentum of the particles. Okay, I know the people here doing more, coming from more the astro side, they are not used to this type of treatment, but I'd like to highlight it anyways, especially because what I think it's important to extract, even if you are never doing this calculation yourself, it's what goes into this calculation. The cross-section. The cross-section tells you what's the relative, like how strong this particle interacts with that, more or less, roughly speaking. We also have this relative velocity between their motion, and then we have the target density distribution, which is kind of obvious, right? Because if you have a lot of these, the chances of interactions is higher. Okay, just rewriting this expression here. Sometimes you can see this expression in a much more convenient form, depending on what you are interacting with. So, for example, if you are doing interaction with photons, and I should stress that interaction with photons, it's a very common case because photons are extremely abundant, and there is also things like the CMB, which is everywhere. So for interaction with photons, the relative velocity here, which I've shown in the previous slide, it becomes 1 because the photon has no mass, so these terms cancel out. Then we also have that beta 2 is equals to 1. And then if we do a change of variables using that variable s that we had before, we can rewrite it in a more convenient way. I just wrote it in this way because you see this in papers sometimes in this form, but the equation is the same. You just have to do a change of variables, okay? I don't want to complicate things unnecessarily. But there is one thing that's very important here, and notice that here I just wrote the integral sign, but here I wrote explicitly the limits of integration. Why did I do that? It's because, and this is the bottom line of this slide, is the limits of integration are important here because not all combinations of energies and angles are possible. Only some combinations of energies and angles are possible here. Which combinations? We are going to see that later. But here, for example, you have a minimum energy of the background that matters. And how do we know that? Well, sometimes if you have a process like A plus B going into C plus D, okay, let me say that B is a photon. So just to keep consistent with that. At the end, if these particles are massive, if they have a non-zero mass, well, you need at least this to have enough energy to generate corresponding to the masses of these particles, right? Since these particles, they have a non-zero mass, your photon has to be massive enough, considering also the mass of this particle, to be able to generate particles with a given mass. So, for example, if this particle MA is 0, and we just have the photon has to have an energy much higher than the sum of the masses. This is obvious, right? Otherwise, this reaction cannot happen because there isn't enough energy, rest energy or rest mass there. And this, the threshold thing, it's very important, and this seems quite abstract now, but I'm pretty sure that everybody here, at least those of you who are working on cosmic rays, have heard of the GZK effect that we are going to talk about. The GZK effect is exactly this type of effect. It's a threshold effect related to the production of a given particle in a given reference frame. Back to this. Okay, I should have deactivated the building part, but yeah. Okay, so there are a few interactions that matter. So suppose we have a cosmic ray nucleus with mass A and atomic number Z. If it interacts with a background photon, so gamma BG background, one possible thing that can go on here is it might remove a neutron out of this nucleus. This could happen. It's a normal nuclear process. We could also have this one removing a proton, or this one just, getting a gamma at the end. There are other things that could go on as well. So this process, it's called photodisintegration. So the photon is inducing the disintegration of the nucleus. Another common process that can happen, it's this Bethe-Heitler pair production, in which we have a nucleus, once again, atomic mass and atomic number, interacting with a background photon, generating, well, the nucleus continues to exist. It's as if this photon converts into an electron-positron pair. This type of reaction, it's very common. So for those of you who do like more particle physics, I'm pretty sure that you've seen this many, many times. Essentially a photon converting into an electron-positron pair due to some external field. Then, well, if you're talking about nuclei, of course, nuclei decay sometimes if they are unstable. Some nuclei are not unstable, but many are. And in this case, we could have like an alpha decay, some versions of beta decay, the gamma decays, and so on. And what's interesting to notice here is that now we start to generate other particles as well. Not only are we changing the nature of this primary cosmic ray, sometimes like here, you're generating another nucleus. So the particle, the cosmic ray that leaves the source is another one. But we are also generating other particles. And these other particles, they continue to travel to here. So whenever we detect a particle at Earth, we cannot be sure whether this particle that we are seeing, it's the primary or a secondary. So we need to know our models quite well in order to answer those questions. And here we start producing like neutrinos, electrons, gamma rays, and so on. And finally, another process that I was missing is like a photon pion production, which it's essentially we have a proton or a nucleus, generically speaking, or yeah, in this case, we just consider that a nucleus is a combination of nucleons, and it can produce pions. And the decay of pions can produce photons or neutrinos, and the muons that are produced here, they decay. We've seen this type of process the first day for the atmospheric, for the air showers. So this type of decays. So yeah, this same thing happens in the universe. Okay, so the question, coming back to the question that we were trying to answer. The interaction length, it's the relevant quantity. The interaction length will tell us how far a particle can travel in the universe, or the mean-free path. There are several definitions, several distance measures for that, but here I'm using the mean-free path whenever possible. Let's take a look at this plot here. Seems a bit messy, but take a look at the colors. So let's take a look, for example, let's start with the black. The black is a hydrogen nucleus or a proton, a single proton. In this case, well, since it's a single proton, there is no photodisintegration because that's a nuclear process. But the other things can happen. And the way to read this plot is the following. Here we have a length, and here we have the energy. So if someone tells you, I detected a cosmic ray with 10 to the 21 electron volts, based on this plot, can you say that this cosmic ray came from, I don't know, 500 megaparsec, which would be somewhere here? What do you think? No. Why? Yep, exactly. So it's attenuated. So the way to read this plot is the following. If we detect a particle here at Earth with a given energy, let's say here 10 to the 20, 10 to the 21, or whatever, we come here, let's say 10 to the 21, and let's suppose we know it's a proton, although it's not, we cannot usually know that, but let's suppose we do. We come here to this line, and then we go here, we see the corresponding length, and this corresponding length would be like less than 10. So the source of this particle has to be at a distance of less than 10 megaparsec, right? And this kind of limits a lot how far we can see with cosmic rays. That's why cosmic rays are not a messenger that can probe the universe very deep down. So if we go here for the protons again, we also see these underlying lines that correspond to the different processes. We see, for example, the dashed line, it's photopion production. It kind of dominates the high energy part of the hydrogen or proton curve. We also have Bethe-Heiter pair production, which is this dotted line. It starts to take over at slightly lower energies, right? And here it's the size of the universe effectively, so at below 10 to the 19 electron volts, effectively the cosmic rays can just travel the universe without undergoing too many interactions. Same thing for the other type of nuclei. We have here, for example, an iron nucleus. The iron nucleus, we should come here. We take a look at this yellow line, and same thing, but now there is the photo disintegration process, so there is like a dash dotted line, which I cannot see. Ah, yeah, it's here. So it dominates most of the time at the high energy part of the iron nucleus. At the low energy, we have on other processes taking over. Okay? So this type of plot, I always like to stress the importance of these plots, how to read them. I'm doing this for cosmic rays, but if you're doing gamma rays, this is your gamma ray horizon. If you're doing neutrinos, you don't have this problem usually, unless you're doing extremely energetic neutrinos, in which case they do interact a lot. Yeah, but if you're doing gamma rays, you have something similar, but you change the processes, right? If there is some new process that we don't know, you just have to add to this curve and see how things behave. And once again, I'd like to stress the role of this process in the creation of secondary messengers. Look at the reactions on the right-hand side. We have some in purple, some in green. Like the ones in purple, they will lead to the production of an electromagnetic cascade in the medium. In this case, usually the intergalactic medium or whatever. And we also have the production of neutrinos. There are many ways to do that. And therefore, these are the cosmogenic neutrinos and the cosmogenic photons that I mentioned before. Okay. So this plot here, it's showing us the measurements, the spectrum, right, in units of electron volt square per square meter per steradian per second, okay, according to several types, according to several experiments, above 10 to the 15 electron volts. What we see here is that there is something interesting going on here, right? There is a change in the spectral index, which I did not have too much time to talk about, but anyways, but what I want to say now is that this spectrum, it cuts off. There is a spectral suppression at the end. Many people thought this spectral suppression at the end of the cosmic ray spectrum would be the so-called GZK cutoff, right? The GZK cutoff, it's this process that I wrote here. It's the process, so we are talking about energies close to 10 to the 20 electron volts. So we would need to have a particle like a proton interacting with a background photon field, producing, of course, this is just the main channel, okay? There are channels that don't go through this delta plus production, but this is the most common one, producing ultimately pions and neutral and charged pions. And neutral and charged pions, again, produce neutrinos, photons, electrons, and so on, cosmogenic particles. Sometimes these particles are called GZK neutrinos or GZK photons if they are produced via this mechanism. So the question is this suppression? We are seeing a spectral suppression. People actually saw this spectral suppression if you do the calculation of the threshold for this reaction to take place, you're going to see that this is very close to 10 to the 20 electron volts, maybe 10 to the 19.8 electron volts or so. So a very reasonable thing is, if you have a theory, or if you know a process, you start with the simple assumption. The simple assumption is cosmic rays are protons. Simplest thing to do, instead of just saying that they are heavier nuclei. And imagine yourself in 1960-something, right after the discovery of the CMB. You'd say, okay, if there is a photon field permeating the universe, I can come back to those equations from the previous slide, and then I can see what are the thresholds for this interaction to happen, because this production, this process called photopion production, it would kind of kill off most protons due to interactions with the CMB. If you're in the 60s, after the discovery of the CMB, it's quite natural to think that. And that's actually what Greisen, Zatzapin, and Kuzmin, GZK, they did. These are actually two works. Greisen did it, and then Zatzapin and Kuzmin did it separately, but in the same year. And they thought about this. They saw that this process, there should be a cutoff in the cosmic ray spectrum due to photopion production at 10 to the 20 electron volts. Actually, it's like 6 times 10 to the 19 or so. And then, later on in the 2000s, we see a cutoff in the spectrum, right? And this makes total sense. Look here at the line for proton. Here there is an inflection point, kind of. The line for proton, it starts to go down very fast above this energy. This is the GZK effect. The question is this suppression that we are seeing now, the GZK effect? And now I like to just make a quick epistemological interlude for that, because, well, in 2008, there was this publication by the Pierre Roget Observatory, observation of the suppression of the flux of cosmic radiation above 4 times 10 to the 19 electron volts. Okay? They are saying that the data are consistent with the prediction by Greisen and by Zatzapin and Kuzmin. Okay? They are saying this could be the GZK cutoff. And then there was this publication by Harris, first observation of the Greisen, Zatzapin, Kuzmin suppression. Okay, why did I call this an epistemological interlude? Well, because there is something to discuss here with these two things that were published in the same year, 2008, both of them a few months apart. So what's the difference here? This one is saying that this is definitely a GZK effect. This one is just saying that this is consistent but not strongly making the statement. So what I ask is the suppression that we are seeing in the previous plot due to the GZK effect or not? So the necessary conditions for it to be the GZK would be what? So, well, either the source spectrum is very well understood such that we can really say that it's the GZK cutoff, but with the statistics that we had at the time and that we still do, it's impossible to say that. We need also a source to have a maximum energy that goes beyond the GZK, of course. But the main point that I'd like to highlight, the GZK effect, if you just read the papers, like this cutoff at this particular energy, it requires a dominant proton composition. The composition of cosmic rays at this energy, well, it's very unlikely that protons dominate, according to current results. Of course, things may be wrong, but then it's another story. So what we are seeing is a suppression in the spectrum that just by chance happens to be at the same energy of the theoretical prediction of the GZK cutoff, but which doesn't seem nowadays, for this reason, to be due to the GZK cutoff. In that case, that suppression, it's just a coincidence. It's just probably, within this interpretation, it's just probably the sources, the cosmic ray sources, running out of power to accelerate cosmic rays beyond that energy. But I'd like to highlight here dominant proton composition. So this statement is correct. The data is consistent with the GZK cutoff. But you cannot state clearly that you are seeing the GZK cutoff, because in order to state that you are seeing the GZK cutoff, you have to prove that it's protons. And you cannot prove it, or at least you could not at the time. And nowadays, actually, the data does strongly disfavor that. Okay, so, well, I think I'm going a bit slow. Okay. Cosmological radiation field. So the equation that I've shown before, I wrote the expression for lambda, which is the mean-free path, or typical interaction length. The things that go in there, the density of photons, of targets, or if you have gas, it would be the density of gas and so on. The density of targets, the cross-section, it's another thing that goes into that. But the density of targets, one common target, as I said, are photons, so radiation fields in the universe, right? They come into this part, and they are essentially for the propagation aspects, for understanding propagation. This plot shows a collection of different cosmological photon or radiation fields. The one that we all know is the CMB, right? Stronger colors are these backgrounds at present time. Weaker colors are at early times, like this. This is at present. This is at present, and so on. So these lines are the cosmic microwave background. And here we have, for example, the cosmic radio background, which is not that relevant, but it's still there. I just would like to show it for completeness. There are backgrounds in other wavelengths. And this one, it's very important for the people doing gamma rays, especially the extragalactic background light, often called the EBL. These uncertainty bands here, it's because, well, there are models. It's not like the CMB, which we know the analytic form. There are models for these things, so there are uncertainties. But yeah, look here, the CMB, more or less the peak of the CMB distribution is at like half of a milli-electron volt. Here we have this extragalactic background light extending up to more or less 10 electron volts. And the radio background, it's at much lower energies. Okay, these ingredients, you should always consider them when trying to calculate those mean free paths from before with that equation. Sometimes what's going to happen is that you already kind of have an intuition, or you know for some reason, or because someone told you, your supervisor told you this is not relevant, and usually you believe, but you should not always trust, because people don't always tell you the right things. You should always understand why they are instructing you to ignore one of these backgrounds. But yeah, sometimes like this one, for example, it's not really relevant for cosmic rays below 10 to the 21 electron volts. If you imagine that there are cosmic rays with 10 to the 22 electron volts, this one could start to become relevant, but not dominant. Okay, we also have galactic radiation fields that can affect the propagation of even gamma rays or cosmic rays in our galaxy. So here we have, for example, the CMB. Here we have the EBL, according to several models. It's this, no, just one model, sorry, of the EBL. And we have this thing called ISRF, interstellar radiation field, which is a radiation field, not a cosmological one, but a galactic one that pervades our own galaxy. And this one does act as target for cosmic rays interactions and for gamma ray interactions. Although, quite often, I would say that this is in general subdominant for cosmic rays. Okay, so one of the ingredients that go into that equation, that's the NDP, or the ND epsilon that I called, which is the density of the targets. That's it. So the other ingredient that we have is the cross-sections that I mentioned before. And now things start to get a bit more messy because the cross-sections, well, especially if you're an astronomer, I know that many astronomy courses, they don't spend time teaching these particle physics things, but it's important to understand a few things about cross-section. So here we have the cross-section for an interaction between a proton and a photon, right? And this epsilon r here at the bottom, it's the energy of the photon as seen by a proton at rest, okay? So this is not the most intuitive thing to imagine, at least to get an intuition now, but this is very convenient when we are working with this. This is a very good frame to create tables and everything, because you just create one table that you can use for everything else. Okay, so this, again, energy of the photon in the proton rest frame. And here we have the cross-section. What we are seeing here is a collection of several processes. Some of these processes we mentioned before, like these ones. We mentioned this before. For example, this one here, it leads to the GZK that we just talked about. And here we have some measurements, but yeah, I'm not going into details about the measurements. But what matters here is the following. We have peaks. We have a few peaks here These peaks are the so-called resonances. These resonances are very short-lived particles, like these ones here, delta plus, delta zero, which decay very quickly into other particles with longer lifetimes. We also have this yellowish, I cannot see this very well, this yellowish line, which is like the direct production of pions. So you just keep this thing here and produce a pion. In the end, sometimes you can produce more than one pion. And how do you decide what's happening? Well, this curve captures everything. Sometimes, if you are in this regime here, there is a dominant one. The dominant one, it's the resonance production. But this one can also happen 1 in every 5 times, more or less. Right? So if you were writing a code for that, you draw a random number. Sometimes you'd get this yellow line. Most of the time, you'd get this red one for a fixed energy. That's how you interpret these cross-section plots. And you have several types of channels that tell you what happens in the end. This channel here goes to the production of resonances. Here, it's a direct production of pions. Here, we have several pions being produced at once. And if we add them all up, this is the total cross-section. Is it clear, especially for those of you coming from an astronomy background, first time seeing that? Or? Okay. Next thing, we also talked about nucleus-photon interactions. Now, before I talked specifically about protons because it's an important case, but we also have nucleus-photon interactions. Once again, here we have epsilon r, which is the energy of the photon as seen by a nucleus at rest, a nucleus with atomic mass A. And basically, in this case, the cross-section is dominant. There are 2 regimes that we can easily identify. There is this blue regime, the GDR, giant dipole resonance. The name doesn't really matter too much. And here, it starts to go into the photon-meson regime. And this plot is here for a very interesting reason, because, well, here we have photon disintegration. We started talking about it earlier, right? I've written down these equations before. There is also a second cross-section peak here. Well, it's not really a big peak, but it's there. But here, for high enough photon energies in the nucleus rest frame, we have the delta resonance production, so photon-meson or photon-pion, as I just talked in this slide. So in that case, the nucleus starts to behave as a collection of nucleons. And then you can use this type of treatment there. Of course, it's not exact, but there is always some scaling relation. So you take the number of protons and the number of neutrons, and you can always relate it to the total cross-section. But yeah, the reason I'm showing you this is that it's important to understand that there is always a dominant channel for these things, but it's difficult to state. You cannot always say, this is the only one that happens. No, it depends on the energy. So now we already know what are the ingredients. So the radiation fields in the background, we know how nuclei interact with photons as well. And I'd like to do an exercise with you. Before, maybe this is a bit out of order. I apologize for that, but let me go to the board because I think it's easier to explain now. So we are talking about the production of a nucleus, right? So in my notation here, capital P, it's a 4 vector for an energy E and a momentum P. So in this case, I just like to do a very quick exercise to understand the concept of thresholds again. When does a nucleus break down when traveling in the universe? So what's the threshold for this reaction to happen? Let's start by writing down the 4 vector P here. And since we have an interaction of the type a nucleus plus a background photon going into, whatever, I'd like to know what's the threshold for this reaction. So we start off by calculating that S. S is the squared center of mass, energy of the system, right? So let's calculate S first in the frame that we are looking at this process. So in our lab frame, here we are looking at the universe. That's what I'm calling the lab frame. Let's do this calculation. So in this case, we would have the mass of the nucleus So that's what I wrote here on, and maybe I should be consistent with the notation. Yeah. So that's what I started writing here. You have Z protons and A minus Z neutrons. So we write that. This is the, what I'm writing down is the expression for S. I don't know if you remember that from before, but in the case of the interaction with a photon, that would be oops, I'm missing the energies here. So energy nucleus where theta is the scattering angle. I've shown this in the beginning, if you recall it correctly. So this is the expression that I'm using as basis for this calculation. So once again, what I'm doing here, I'm counting the number of protons and number of neutrons to get the rest mass term, so the first term of this equation. Now, there is also this other term that corresponds, look, is that correct? Yeah. So there is this other term here, which corresponds to the second one, the factor 2 and the energies, right? So, yeah, same thing. Maybe I should call this, let me call this mass nucleus just to make it easier. Yeah. So, before I proceed, before I forget, notice that here we have the orange part and the green part. I'm doing that because there is this nucleus rest frame. We are working in the nucleus rest frame here, okay? So since S, the squared center of mass energy, it's a relativistic invariant, what I'm arguing here, what I'm trying to show so that you can follow better, is that if I do this calculation in these two frames, in the frame of the lab, the frame that we are seeing here right now, and if I do this calculation in this other convenient frame, which is easier to work with, we can extract some meaningful results. That's what I'm trying to do, okay? So I'm trying to see what's the energy that a nucleus should have if we look at this plot in order for a reaction to happen. I could have done this for any other of the processes that I mentioned before. I just decided to do this here. I don't know why, for no reason. Yeah, maybe I can go faster. Are you following? Yeah? So maybe I don't need to write this because it's already written at the board. But then we have here the rest mass of the nucleus. It's this first term. The second term here, now comes this. It's 2 times the energy of the nucleus, but in the rest frame of the nucleus, the energy of the nucleus is just the mass, which is this term, mc squared. The mass of the nucleus, c squared. And here we have epsilon prime, which in this case, it's epsilon r. Sorry about the notation, it's inconsistent, but epsilon prime, it's this epsilon r, okay? Same thing, in green. Now let's look at the other side. At the other side, this is the lab frame. The non-primed is the lab frame. This is what we are measuring. We are measuring a nucleus, and now we are measuring a nucleus with energy E, and it's interacting with a photon, a background photon of energy, epsilon. And there is this angle, this scattering angle between them, right? So one frame, the nucleus rest frame, our lab frame, and now if we just solve these two equations, these two things are equal because this is a relativistic invariant. It doesn't change if you go from one frame to another. If you just make some simplifications, you get that the energy of the nucleus in the end, let me just erase this. you get that the energy of the nucleus in the end is given by this. So this is the threshold for one of these reactions, right? An exercise could be, if you are interested, to do the same thing for the GZK effect. If you do the same thing for the GZK effect, and you calculate this energy, you're going to get something like 10 to the 20 electron volts. Actually, this is a very instructive exercise, and when I teach this, you know, this was in my last exam, so yeah. But this is a very interesting exercise to do. So what's the energy that a nucleus should have in order to interact with a photon background? So this gives you the threshold of the reaction, okay? It depends on the angle, so you can just make some, the maximum or the minimum value, you can just play with the value of theta here, just assume that it's 0 or 90 degrees, for example, and so on. One example only for now, but these, you can apply the same type of strategies many times to any system that you have. Okay, you just use the fact that S is a relativistic invariant, you calculate the form momentum in one frame, calculate the form momentum in the other frame, you say that they are equal, and then you solve for the energy. Finally, the last part of interactions, it's this. We can also have like proton-proton or nucleus-nucleus interactions. Let's talk about proton-proton first. Proton-proton interactions, it can lead to the production of many pions. And again, you know, there is no astrophysics in what I'm saying. I'm just talking about particle physics for now. It depends whether I apply this to intergalactic space or to the atmosphere, because this is exactly what we saw in the first lecture. We have interaction, not exactly because we have air, but it's very similar. We have the production of a bunch of pions. And here we have some cross-sections for these processes. Yeah. And back to this equation. This, I think, it's the most important equation of, for propagation, at least for the interaction part, because it contains everything that you need to know for interactions. In this case, only with photons. I'm not talking about interaction with gas. It becomes slightly more complicated if you have a gas distribution. Or simpler, because sometimes the gas you don't need to consider. You can remove one of these integral, or you can remove the integrals, because the gas is usually monochromatic. Quite often people assume that, even though it's not exactly true. But again, you have interaction thresholds. These interaction thresholds, you can compute them like, oops. You can compute interaction thresholds in this way. You just solve for epsilon instead of solving for this. That's how you compute interaction thresholds. Same thing, just pass this epsilon to the other side, this energy to this side. Okay? And yeah, interaction threshold here. Also, this one depends on the energy of the particles. So S max is actually, if you think about it, for interaction with photons only, you just take that, the mass of the particle, of the incident particle, and now theta can vary between 0, cosine theta can vary between -1 and +1. So it's easy to see that sometimes you can get like 1 plus beta. For relativistic particles, beta is almost 1, so this becomes a 4. And if the particle is highly relativistic, this term is also much less than this one. So these are approximations that can be used. Okay, first term, it's the interaction length. I do hope you understood how to read these plots, because I consider this the central part of the interactions here. Okay? Then we have the photon backgrounds here, several types. We have the cross-sections, and that's what we compute, and that's how we know how far a particle can travel. So the typical attenuation length of a particle. Whether it's a gamma ray, a cosmic ray, or whatever you are doing, interacting with photons in this particular equation can be easily extended. Questions so far? Yep.
In this first plot, I would expect like the heavier nuclei to get attenuated faster, but here I'm seeing the opposite.
To get what?
To get attenuated
Faster.
But I'm seeing the opposite here. Am I understanding?
You are understanding correctly, because, so let me go back here. Yeah, this is a good question, because So for those of you who haven't heard his question, he was saying that in this plot, he expected the heavy nuclei, like iron, to be disintegrated faster than the others, than the lighter ones like helium. Like a proton, yeah. Well, the proton doesn't disintegrate, but in this case, the helium, yeah. In this case, what really matters, so the equation here contains the cross-section. So it's not just about how massive, it's about the cross-section as well. The cross-section drives this, this process. So it's not straightforward because the cross-section here for different types of nuclei, they are not the same. This is an example for iron, but if you take this for helium, I don't know how it would go, but it explains the difference. So the difference comes from the cross-sections in this case. It doesn't scale linearly.
But it's more the cross-section seems more dominant than the mass of the...
Oh, then the mass, definitely, yeah. Okay. Yeah. So the cross-section is very important. So you cannot just ignore the cross-sections here. So if you change the type of particle, even though it's just another nucleus, you would naively expect that, you know, a helium nucleus, it's like, would behave like 4 protons, more or less. And then, you know, or 2 protons, 2 neutrons, 4 protons, 2 neutrons, yeah. For 2 neutrons, 2 protons, and then nitrogen like 14-7. Yeah, but this is not necessarily true. Because of the cross-sections. The cross-sections, they behave differently. And there is a reason for that. The way you usually think, you can think of a nucleus as a bunch of nucleons, a bunch of balls glued together. If you have like a helium nucleus, it's just 4, right, the stable isotope. So if it's 4, it's easy to interact with the 4 nucleons. But as the nucleus starts to get bigger, the size of the nucleus grows with the volume. But the area, it's what matters for interactions, right? So the surface of the sphere. And what's inside, it's kind of shielded from the outside, so it doesn't scale. Kind of, yeah. That's, yeah. Intuitively, that's the way to think of it. Yeah. So now, let's move on. So more questions about this interaction part? No? Okay. So now we have half an hour, that's good, and we got to the magnetic field part. So the next ingredient that we need in order to model the propagation, well, here, magnetic fields, it's one of the things, and I think this is also very important for people doing cosmic rays. For people doing gamma rays, well, arguably, although this is debatable, not so much. But for cosmic rays, this is important. And this part, it starts to become also very messy because magnetic fields are not well understood in the universe. So what I'm going to do now is first tell you a bit about magnetic fields in the universe, very briefly, and start, because I know I won't have enough time, and I will start showing you how the theory of cosmic ray transport in magnetic fields, okay? So, let's talk first about extragalactic magnetic fields. So, the naive question that we would all be trying to make here, this is an astroparticle school. Whatever messenger you are dealing with, in our case, now in this lecture, cosmic rays, well, why can't we just look at a particle and say, okay, let's try to correlate this with the source? Well, if you're doing neutrinos, that's kind of straightforward, right? The neutrino, in principle, if you assume that it was produced in a source, it would point directly back to that source. Gamma rays, because of the cascade process, there is an electron component, and then the gamma rays would be scattered around. But cosmic rays, they are very deflected by magnetic fields. So that's why we cannot, it's very difficult to correlate arrival directions with sources. Magnetic fields, especially outside our galaxy, they are not well understood. But the question is, okay, we don't really know them, but can we take them into account? And does it make a difference if we just try to model everything with several types of magnetic fields covering all possible uncertainties? Well, not really, because let's understand how magnetic fields are distributed in the universe. So this is an animation of a cosmological simulation of structure formation. This is like maybe 200 megaparsec-ish. I don't remember the exact number. It's been like almost 8 years. I don't remember. But what you are seeing here is the following. You have these circles. These are clusters of galaxies in the universe. And then these clusters of galaxies, they are connected to each other through these filamentary structures. They are the so-called filaments. Well, very creative name. But notice that most of this is black. And why is it black? Because most of the universe is made up of voids. It's empty. Structures like galaxy clusters or filaments, they don't take most of the volume of the universe. Most of the volume of the universe, it's empty. It's all black out there. These regions are the so-called cosmic voids. So if we try to constrain magnetic fields in cosmic voids, the available parameter space, if you take a look at how strong they are and how the typical length at which they act, and we are coming back to this, the so-called coherence length, it's shown here. So the white region, it's the available one for magnetic fields in the voids. And you don't need to understand too much about this plot. Just notice that the uncertainty in the strength of magnetic field in voids, it's somewhere between 10 to the minus 9 Gauss and 10 to the minus 15 Gauss or so, if you trust these lower limits, which are not necessarily 100% reliable. So we are talking about 6, 7 orders of magnitude vertically, plus several orders of magnitude horizontally. Yeah, you cannot say that they are really well known, I think. And this is for, I'm showing you this because this corresponds to what is expected for the black regions here, the cosmic voids, which compose most of the universe. So honestly, what are the odds that a particle that's coming from far away in the universe, from an extragalactic source, will travel just through the filaments? It's extremely unlikely. So most of the volume of the universe, it's made of voids, and voids are not well known, their magnetic field. Actually, we are not even 100% sure that they have magnetic fields, which would be good for cosmic rays. Okay, well, that's out of place, sorry. Now we have the galactic magnetic field. The galactic magnetic field is also very important for understanding cosmic rays, not only the cosmic rays at low energies, which remain trapped in our galaxy, but the cosmic rays at high energies. So I'm going to show you just a couple of examples of what happens with cosmic rays when with high energy cosmic rays in general, due to the galactic magnetic field. So in this example here, on the right, I'm showing you the average deflection in each one of these pixels of this map according to one model of the galactic magnetic field. This number here at the top, it's the logarithm of the rigidity. Rigidity, for those of you who are not familiar with the term, well, in this case, in this particular case, we have rigidity. Something like energy over charge. So yeah, rigidity is energy over charge. So what you are seeing here is the log of rigidity. So this is essentially the energy of a proton. You can think of it, or of an electron. And this is the average deflection in a given pixel looking in galactic coordinates, like the galactic plane is here. What we are seeing here is that, okay, start again. Okay, we start with low energies, like 10 to the 17 electron volts. Low energies, but still high energies. We see that the deflections are like 90 degrees, so it's completely isotropized at low energies, or low compared to ultra high. And as energy increases, here they are still completely isotropized. But as energy increases, there are these blue regions where deflections start to become low. And now, a new window starts opening up for cosmic rays, because now cosmic rays will start to correlate with the position of the sources, or at least not to be so uncorrelated as before. But this only happens at the very high energies, as you can see. Let's take a look at one specific case, Centaurus A. Centaurus A is an active galactic nucleus, the closest one to Earth. It's located at about 3.7 megaparsec from Earth. And it's shown here as a diamond. Again, what we are showing here is rigidity, or the energy of a proton. So as rigidity or energy increases, you see that the direction, arrival directions of the cosmic rays from this object starts to get very close to the position of the source, right? This is an kind of imaging effect. And at the highest energies, it goes directly to that position. But notice that at 10 to the 18 electron volts already, it spreads over 30 degrees, 40 degrees. The spread is huge at 10 to the 18 electron volts. So it's not really possible to just correlate arrival directions of cosmic rays with the sources for this reason, because magnetic fields, and this is just the galactic. Okay, I talked about the extragalactic. This is the galactic magnetic field. Okay, and this, just for the record, this source, it's the closest AGN, 3.7 megaparsec. It's nothing. It's a very nearby source, I should say. The simulations were obtained with CRPropa, just for the record. Okay, maybe I can skip this since I don't have time. Yeah, I'd like to talk a little bit. I'm going to come back to this. Maybe I should leave that for tomorrow, okay. Yeah, I'd like to do a little bit of, to explain a bit of the theory of propagation in magnetic fields. Okay. So far so good? You're following? Main ingredients, how to read the mean free path plot, everything? Okay. So now things are going to get a bit more complicated for maybe the next 10 to 15 minutes, and then it's going to get more complicated tomorrow. Where's that chalk? So let's suppose the following. I know that you all know that, but I do have a point. I promise this does seem simple, but I like to build it up. So we all know the Lorentz force equation. Right? This is the Lorentz force equation. And then let's suppose that we have first case, a homogeneous magnetic field with the same value everywhere. So if we have a homogeneous magnetic field, let's say, for convenience, I'm going to call this B0, the absolute value, and I'm going to say that it's in the Z direction just to make the calculations simple for me. Okay, it's straightforward to get the equations of motion out of here. So we can write, for example, and of course, the Z component is going to be 0 because there is a vector product. Okay, now it's convenient to introduce something that we call the gyro frequency. Which is defined, in this case, as, well, the charge, actually the absolute value of the charge, to be honest. Right, and then I can write this in the more convenient form. Using the gyro frequency in this convenient form. This is straightforward, everybody knows how to do that, I'm pretty sure, but there are a few concepts that can be introduced here. Next concept, the so-called pitch angle. Pitch angle, it's defined phi p. It's defined. So, of course, there is an energy dependent, a time dependence for the velocity. this is another useful concept. So we have the components that are perpendicular and the components that are parallel to the magnetic field, and then we can define this pitch angle. Okay. These are very simple definitions, and this is a homogeneous magnetic field. There is no challenge here. But now let's complicate things a bit. Or actually, let's just, before we do that, we can also write down the equations of motion. So we can get out of dv, we can get x, y, and z. So if we just write down the equations of motion, and we have to write the same thing for y and z. And, of course, the z component, okay. So one thing is obvious. If you just do x squared plus y squared, this is a constant. Right? Because, well, we have sines and cosines there. And you can identify something, an interesting thing here, which is if you find a center in x and y coordinates here, if you just define, you can define here, x center. So x center is going to be x0 plus and you have y center. So I'm just saying that this thing here, it's kind of a center, just a convenient coordinate system. Okay, I'm mixing these my phi's, right? There, we just write in the same style. This is not the pitch angle. This is just a phi. Okay. Why am I writing this? Because now we can introduce a concept that's called the Larmor radius or gyro radius. Because now we have defined, we found the equations of motion, we know how this evolves with time, and we can define the Larmor radius. It follows immediately from here. Once we have the center, you can see that for this simple problem, your particle is just spiraling around with a constant radius, and this radius is given by the Larmor radius, which is this. Right? Or, in a more convenient form, if you just do E is equals to gamma mc squared, okay, simple case, done. There is no challenge. This is basic physics 3 for everybody. But now we can do second case. The second case, we are going to add a perturbation, yeah? No, not yet, not yet. Yep. Yep. Yes, you are right. For this homogeneous case, yeah, but I'm separating it because now I'm going to add a perturbation. Yeah, but for those of you who didn't hear what he said, he was asking if this phi and this phi is the same. Quite often, for the simple cases, it's true. But now we are going to do a case in which it's not. And that's why I introduced the phi over there, the pitch angle. Because now we are going to add a perturbation. So I'm going to say that the magnetic field, it's that simple magnetic field from before, plus a perturbation. So this can be and I'm going to assume that this perturbation is perpendicular. So it's essentially restricted to the XY plane. And now this is where things complicated. Let me see the time. Okay, I should stop in 3 more minutes, maybe, or 5. So simple case, homogeneous. Now we have all the definitions that we need. We add a perturbation perpendicular to that. And now the equations of motion, they actually become quite complicated. I should have written them at the board, but I'm going to just write them there in the slide, but I'm just going to write them here. Omega 0, now, I'm just calling 0 to ensure, to make sure that it's the same as the homogeneous case, okay? Just for... Okay, I'm also just writing this for completeness because it doesn't add a lot. Okay, so this is more or less how we start now for the perturbed magnetic field. We start to change the equations of motion to see what happens. So in the previous case, what we had was this helical motion like that with a constant radius. But now we have a perturbation. So the radius is no longer going to be constant. So, and things, actually the motion is going to be sometimes tilted. You know, so it's going to be slight. Before it was like this, and now we might have like the radius changing, the direction changing a bit because we are adding perturbations. And I'm going to just make the argument and then stop. And why am I writing this? It's because, well, quite often in astrophysical environments, we have a background magnetic field like which is turbulent. You know, there are things there that are mixing. Magnetic field is randomly, almost randomly oriented. But on top of that, sometimes there are regular magnetic fields. Like our galactic magnetic field, it has several components. One of the components is like a regular. It follows the spiral arms of our galaxy. It has to do with the process of structure of the formation of our own galaxy and its history. But on the background, due to plasma effects, magnetohydrodynamics, I'm not going to go into those details, but there is this background plasma that creates a turbulent magnetic field. So what I'm aiming at here with this thing that I called perturbation is to describe turbulent magnetic fields. I started with the simple case. I made you think that you can follow it, but now you probably won't be able to, because I'm not also able to do all these calculations easily. I always get them wrong. But I'm just joking. I mean, they are feasible, but you know, there are many small details. And that's what we are going to follow up tomorrow. So now that we know we built up this perturbation, tomorrow we are going to do this turbulent case. The turbulent magnetic field, we are going to characterize the magnetic field and describe the motion of cosmic rays in a turbulent magnetic field. Because we know that the regular component of a magnetic field, just a homogeneous one, would just deflect a particle, Lorentz force, easy. But here, you know, because we have a turbulence And if we assume that it's perpendicular to Z, there is kind of a smearing around that direction in the propagation of particle. And this is very important for understanding the propagation of cosmic rays. Yeah, I'll stop here for questions.
Thank you, Rafael, for a nice talk. We have time for questions before the coffee break. Raise your hands. Yeah, just 1 second. I will give you the micro.
So, such an interesting talk. My question is, when we do simulations with particle in cell, we generally get the image diffuse and we inject particles into this. And then we do some treatment of the particles, right? We get the spectra, etc. What would be the difference of the particle in cell simulations with the Monte Carlo simulations with CR-Propa?
So the particle in cell simulations, you keep re-injecting, so it's kind of non-linear. Here, it's not really feasible to recompute, because here we use the test particle approach. We just do one particle at a time. Then you could ask me, okay, but then you could just compute how one particle propagates and then change everything else based on the propagation of one or a few particles. But this becomes highly nonlinear and computationally prohibitive with the current design. It's not that we haven't thought of it, it's just that we would need to change many things in the structure for that.
Okay, any other question? No? Well, if not, let's thank Rafael again. And we shall reconvene at 11.